Hello everyone, I'm Alessandro Margara from Politecnico di Milano, and I'd like to share with you some reflections inspired by the DEBS Test of Time Award, also on behalf of my colleague, Professor Gianpaolo Cugola. Before entering the details of my talk, let me just say that it is a great honor for us to receive this award. Both Gianpaolo and I are still deeply connected to DEBS, and it is very rewarding to see the impact of our work on the DEBS community. Actually, DEBS 2010 was one of the very first conferences I attended and my first DEBS edition. I was a first-year PhD student back then, starting my research on complex event recognition technologies. And after 10 years, this award is a good opportunity to look back and see how the research in the area has changed and evolved. Let me start by quickly summarizing the context and the main contributions of our research. Complex event recognition is the task of recognizing situations of interest or complex events from a possibly unbounded stream of observations or primitive events. Complex events are defined starting from primitive events using complex event specification languages, which enable to predicate on the type, content, and most importantly on the order and temporal relations between the primitive events. So we want to specify some situations of interest, and we must be clear about what brought us to that situation, which sequences of events brought us there. Our DEBS 2010 paper focused on event specification, proposing a new language called Tesla. Over the next several years, our research targeted many aspects of complex event recognition, including evaluation algorithms, parallelization, distribution strategies, and Tesla represented the foundation of all these works. Here is a quick overview of Tesla. The slide shows a possible definition of a complex event of type fire, starting from the observation of temperature, smoke, and rain primitive events. Tesla offers operators to filter primitive events starting from their type and content. For example, the definition in this example selects only temperature events that carry a value greater than 40 degrees. Combine primitive events into sequences within a given temporal scope or time window. The example requires a temperature event to occur before smoke and within 5 minutes at most from smoke. Then with Tesla, you can correlate the content of multiple events using parameters. The example requires the smoke and temperature events to come from the same area. You can predicate on the absence of events, in this example, the absence of rain using negations. Then you can flexibly decide which events to select and to consume. The example selects the last temperature event occurring before smoke and consumes it. So it is not available for further recognitions. Not exemplified in this pattern, Tesla enables reusing complex events to define other complex events, thus building hierarchies of abstractions. When Tesla was first proposed in 2010, several other event specification languages had already been introduced. I think that the main merit of Tesla was to highlight two key aspects. First, the need for a simple, high-level event definition language to be accepted and adopted even by non-technical domain experts. So we strive to build a reduced set of operators that could be combined in a flexible way, and we propose the event hierarchies as a way to reuse the definitions of complex events to build libraries of reusable definitions for specific domains. Second, the need for such a language to have a precise, formally defined semantics to avoid ambiguities. We provided the semantics of Tesla using temporal logic. By contrast, many existing languages were providing operational semantics that were strongly coupled with the event recognition algorithm. That was 10 years ago, but how is the situation now? How it has changed in the meanwhile? In particular, is complex event recognition still a relevant problem? How is it addressed today? What are the current research trends? So event-based systems are even more relevant today. As software systems grow in size and complexity, they comprise many distributed components, and often these components adopt an event-driven communication paradigm. A couple of examples are microservices architectures, which decompose a software system into loosely coupled components that communicate only by propagating events. On the left of the slide, you can see the internal architecture of Netflix built of many microservices. And then second example, Internet of Things, where increasingly many devices observe events coming from the external environment and from other interconnected devices. In this context, recognizing situations of interest starting from the observation of events remains vital for applications. So the answer is yes, complex event recognition is still a relevant problem, even more today than 10 years ago. How is it addressed today? So over the last decade, many technologies emerged to propagate and process streams of data, such as Apache Kafka, Spark Streaming, Flink, just to name a few. Notice that I use the term data on purpose. These platforms are very good to perform general data processing, and they are not very event-oriented. They provide a very efficient general purpose programming core, which defines the data model plus a low-level programming API accessible through regular programming languages such as Java, Scala, or Python. On top of these core, there are libraries that simplify specific stream processing tasks, often providing a kind of domain-specific language. A notable example is processing and querying relational data streams. All these platforms offer libraries that deploy and optimize relational queries on streaming data. There is a common understanding of the semantics of these queries, and the formalism is converging across platforms as an extension of some SQL dialect. Unfortunately, only few libraries are available for complex event recognition, and no domain-specific language has emerged. In summary, after 10 years, the standardized high-level language for complex event recognition is still missing. So developers still need to implement recognition algorithms using low-level processing API offered, for example, by these platforms. And although tools specifically oriented toward event recognition, such as Esper or WSO2, are available, they are not mainstream as the platforms that I described above. So in my opinion, we are at this point because of a lack of full understanding and agreement on the core building blocks for event specification language and their semantics. In comparison, defining the foundations of relational data stream processing was arguably easier because SQL was already there with decades of research and development on database systems. Its extensions to streaming scenarios built on a solid ground and were widely accepted and adopted. But an equivalent of SQL for events was not available 10 years ago and is still not available today. The good news is that the field is still widely investigated. As an example, I had the pleasure to co-organize a Dagestud seminar on the foundations of complex event recognition in February this year. During that event and in several other occasions, I could see many new contributions coming from various communities, not only the core DEBS community, including database community, logic-based reasoning, knowledge representation community, semantic web and stream reasoning, and many others. In general, I see many steps forward in understanding the foundations and the core building blocks of complex event recognition. This is one of the main problems that Tesla tried to address 10 years ago, and it is very exciting to see that it is still actual today. Just to name a few notable examples, there is the recent work by Gress et al. On the formalization and expressiveness of event recognition, and there is also some remarkable work on recognition algorithms. Also, over the years, many extensions to the original concept of complex event recognition have been proposed. They include formalisms for managing uncertainty inside primitive events and inside the derivation process, integration of inductive derivation, support for event forecasting, just to name a few. We believe that these additions are necessary for several applications domains and so should be investigated even more to foster adoption. So they go in the direction of simplicity, usability of complex event recognition languages. To conclude, we believe that complex event recognition is still a relevant problem today. The lack of an established formalism still represents an issue, but the importance of formal foundations today is widely recognized. Over the last 10 years, there was a lot of research from various communities converging towards a deeper understanding and shared view of event recognition. Moreover, the research also addressed usability by studying additional features, extensions that might be useful in some application domains. We are confident that these efforts will finally lead to mature tools and wider adoption, which was our original dream when writing Tesla. Thanks a lot for attending this talk. I'm really looking forward to hearing your comments after this session and discuss with you ideas for possibly the next 10 years of research. Thanks again.